Our experiment is designed to measure the effect of heat pipe diameter on the speed of its heat transfer. We begin by boiling 200 milliliters of water to keep it at a near constant temperature of around 100 degrees Celsius. Next, we take our first heat pipe, in this case a pipe with an internal diameter of 4.40 millimeters, and attach a surface temperature probe to it, using copper tape. It is then placed in the boiling water. We record the temperature of the pipe and the water over a period of 180 seconds. The pipe is then removed from the water and the process is repeated, only this time using a pipe of internal diameter 20.32 millimeters. We then test pipes of diameters 7.76, 10.39, and 13.86 millimeters, and keep track of our results. The heat pipe is a sealed copper pipe 20 centimeters in length, with roughly 30% of its volume filled with ethanol. As the heat pipe is dunked into the boiling water, the temperature of the copper tube, as well as the ethanol, begins to rise. When the ethanol reaches a temperature of roughly 80 degrees Celsius, it begins to boil and becomes vapor. This vapor disperses itself throughout the tube, filling it. When it reaches the cool end of the pipe, it condenses. This transfers the heat from the ethanol to the copper, thus heating the pipe. Over the course of our experiments, we gained no truly meaningful data, as many of our heat pipes were inconsistent, and 180 seconds proved to be an inadequate amount of time to record, as it improperly represented larger heat pipes. However, here is what we would have expected to see in a more ideal environment. Assuming that the only non-negligible sources of heat transfer are the evaporation of ethanol at the bottom and condensation at the top, as well as radiation from the copper wall of the heat pipe into the atmosphere, the temperature at the top of the pipe at equilibrium should be approximately proportional to 1 plus 1 over d, where d is the diameter of the pipe. Thus, as the diameter of the pipe increases, the effectiveness of the pipe should decrease.